Welcome to the 5th Philip Wetton Lecture in the Department of Physics here at Oxford. I'm Stephen Smart. I'm the Philip Wetton Professor of Astrophysics. This is a statutory chair in observational astronomy, began in 2002. It's a position generously funded by Philip and Roswitha Wetton, who we're delighted to say who are with us here tonight. Philip was an alumnus of Christ Church. He matriculated in 1955, not in physics. He graduated with a BA in modern languages. Philip worked for Unilever, used his considerable language skills in the British diplomatic service before settling in deepest Wiltshire with his wife, Roswitha. The Wetton donation in 2002 helped create a new chair, and the first Wetton professor was Roger Davies, who's here tonight. The Wetton Fund is held at Christ Church, and it funds a PhD, a DPhil student, and a workshop every 3 years. Roger has organised the previous 4 workshops, and it's become a tradition to host a public lecture broadly on the topic of the workshop. Philip and Roswitha are great friends and supporters of the physics department at Oxford, and we thank them for their generosity. Today we had the first day of the workshop on the future of multi-messenger astronomy beyond 2025. The topic concerns the detection of gravitational wave sources by the LIGO and Virgo detectors, and how we can locate these sources in the electromagnetic spectrum. From high-energy gamma rays, optical light, through to radio regime, and we will hear this month, and we'll hear from Patrick, this month sees the 10th anniversary of the discovery of gravitational waves, 14th of September, 2015. 2 large black holes orbiting around each other in a binary system merged in a galaxy more than 1 billion light years away, giving a signal that was detected on Earth, a tiny signal that lasted, as you'll see, 0.2 of a second. A remarkable measurement and discovery for which the Nobel Prize was awarded in 2017. To tell us about this and what has happened since, we're delighted to welcome Patrick Brady from the University of Wisconsin Milwaukee. And Patrick was central to the team who made this discovery in 2015 and many more since. Patrick was an undergraduate at University College Dublin, graduating in 1989, and a PhD student in theoretical physics at the University of Alberta in Canada until 1994. He had 6 years of postdoc at Newcastle, Caltech, and University of California. And he's been at Wisconsin since 1999 and was as a professor of physics and was made a distinguished professor in 2023. Patrick spent most of his career working on the physics of black holes, and most recently, for the last 6 years, he's been the spokesperson of the LIGO scientific collaboration. In 2015, when this breakthrough was made, Patrick was chair of LIGO's Data Analysis Software Working Group. The signal in 2015, just in the first few weeks of LIGO's new sensitivity regime, must have been a wonderful gift to that data analysis group. The paper's been cited more than 12,000 times. The breakthrough discovery is still how remarkable when you consider how tiny the effect is, as we'll hear. These detectors can measure the length of their interferometer arms, which are 4 kilometers, to the fraction of the width of a proton, 200 times smaller than the proton, in fact. So to tell us about this and what has happened in the last 10 years in this exciting new frontier in physics and astronomy, welcome Patrick.
Great, let me just do a sound check. Everything okay with sound? Great. So thank you, Stephen, for that introduction, and it's a great pleasure to be here. So today, just to get started, Stephen's already told you a little bit about my introduction, but I want to remember this 14th of September 2015, so 10 years ago this month, when we measured a gravitational wave from a pair of black holes that collided about 1.3 billion light years from Earth. Now, some of those words may not mean much to some of you. Many of you may be experts already. But as we go through the next few minutes of the talk, I'm going to tell you a little bit about each piece. But before we do that, I want to show you a piece of that signal that we recorded 10 years ago. So on the screen, what you see is our 2 different pieces of data. Along the horizontal axis, going from left to right, is time. It's half a second on the screen. And then each of the panels that is stacked on top of each other, the thing that's showing on them is frequency. Since I'm going to play the gravitational wave signal, you're going to be able to hear two different things. You're going to hear just the changing nature of the signal as the frequency of that gravitational wave sweeps upwards. The nice thing about gravitational waves detected by the ground-based detectors such as LIGO is that they are actually all in the audio band. So we can actually play them back if we want to hear them. So when you hear this signal, you're also going to see a visual cue on the diagram that sort of shows you what the shape of the signal is as it goes, and it's going to repeat multiple times. First time it plays, it'll show it, and the sound will be exactly at the frequencies where the gravitational waves were. And then we're going to adjust the frequency to make it a little more audible and play it again. And then that'll repeat a few times. There was only one wave that came through. So just one of those cycles is all there is that came through that first time. But let's listen to it for a moment. Now for me, that's the most beautiful sound in the universe. But the interesting thing is that when I said those waves came from a pair of black holes 1.3 billion light years away, that means that the waves had been traveling across the universe for 1.3 billion years. So if we put that in perspective, about 800 million years ago, the first multi-celled organisms appeared on Earth. And then, as we kind of go to think about this, it's fun to compare the waves racing across the universe to the evolution of human beings on Earth to reach the capabilities to be able to measure these waves. And so what we next then think of is that at about 65 million years ago, the gravitational waves were passing by the Virgo cluster of galaxies. That was around the time that the dinosaurs went extinct. If we keep on going, then at about 50,000 years ago, the gravitational wave front had just reached the edge of our galaxy. So this is a cartoon drawing of our galaxy. The straight line that's labeled merger wavefront about 50,000 years ago represents the wave that has spread out from those colliding black holes. And this is just a little tiny piece, the little piece that's actually going to go across our galaxy. As the waves continued to race through the galaxy, civilizations on Earth, of course, came and went. And then, about 400 years ago, the wave were passing about the distance of Polaris, the North Star. And that's when Isaac Newton first wrote down his theory of gravity. He explained how apples fall and said that's related directly to the same reason that planets go around the sun and the reason the moon goes around the Earth. Now, looking at this diagram here, the lines on it, the one that moved across, representing the wavefront, it's interesting to know just a kind of how much time they span. So each of those are to scale are about 500 years. So just the start of the line kind of on this side represents about the time when Isaac Newton was born. And about 100 years ago, when the gravitational wave was passing the distance of the star Nu Draconis, which is a not very bright star in the constellation Draco, Albert Einstein introduced his theory of gravity to the world. Now, that theory is somewhat complicated in its mathematics, but you can distill some of the ideas down to get a sense of what it tells us. So it says that we should think about gravity no longer as a force, the same way as Newton had said, but we should think about gravity as a manifestation of the whole curvature of space-time. And in particular, Einstein said, look, there's a rule by which if I know the curvature, I can say how things move around within space-time. And using that method, he was able to figure out how the planets, in his theory, should go around the sun. And in particular, he was able to figure out a slight deviation that had been observed in the perihelion of Mercury and solve that problem. The other thing, however, is that his theory also works the other way. Whenever you have matter in space-time, it tells space-time how to curve. And so there's this intricate relationship between matter and curvature of space-time that is laid out in his theory. Now, he went on to make a bunch of tests. I mentioned one already, the perihelion of Mercury, but he also predicted that light would bend when it passed through a gravitational field, and that was observed by 1919 and then 1921. He also figured out that clocks would actually run at different speeds depending where they were, on the surface of the Earth or up in the sky much higher. And that was measured in the 60s. And he also had a hint from some previous work that there should be in this theory a wave-like behavior. And so he worked through his equations and he showed that his equations did indeed predict the existence of waves of gravity. These are ripples in the curvature of space-time. And in working that out, he did a couple of different things. So I'm going to take two different approaches to this. So the first is the cartoon image that you see here on the screen is representing the two black holes, which we're going to talk more about in a while, going around each other. And as they move around, since matter tells space-time how to curve, it causes these ripples of space-time curvature to propagate out from those things that are going around each other. Now, Einstein worked out the fact that those waves must travel at the same speed as light. He also worked out what they would do as they passed by detectors here on Earth, and I'll say more about that in a moment. And he also worked out a recipe for how to make gravitational waves. And his recipe is crudely captured by this equation. I don't need you to think about the equation too much. What's most important about the equation is that it has in it, when we look at it, it says that somehow the strength of the gravitational wave, which is this Hij, depends sort of on this complicated formula, g, that's Newton's constant of gravity, divided by the speed of light to the power of 4, times a mass, a speed squared, and 1 over the distance to where the waves are being made. And what he basically said was, in order to get a strong gravitational wave, what you need to do is you need to get some matter, you need to make it lumpy, you need to make it dense. So I'm going to do that with my fist. Start out with some matter. I make it dense by squeezing it down. I make sure it's lumpy by kicking out my fingers a little bit here and there. And then I shake my fist like this. And when I do that, a gravitational wave propagates out into the universe, across through you, and out, signaling somebody somewhere that I just shook my fist. So with that in mind, the ideas and the attempts to understand gravitational waves began. It was a very long and really sort of winding path. People for a long time weren't sure if these waves were real or if they were somehow related to the way the equations were written. But in the 50s, people worked out a way to really think about those gravitational waves when you thought about it in terms of a detector. And we're going to represent sort of a very trivial, simple detector for right now. We're going to start out by putting somewhere out in space where there's nothing going on. We're going to put these yellow little balls floating in a circle with a red ball in the middle. And then we're going to imagine a gravitational wave coming from the back of the lecture theater and propagating straight along here and through the screen and continuing on its way. And that wave that we're going to see is going to keep rolling in, sort of like you see waves on the ocean continually going. You get one comes in and breaks, and then another and another and another. And we're going to watch what happens to that ring of particles as those waves go by. So it's good to have a reference. We look at the radius of the circle, and that we're going to designate by the length L. We let the waves go by. And what you notice is they stretch and squeeze in alternating directions and patterns, continuously doing that. You notice that the sort of change, the maximum deviation from a circle to the extended stretched object has a little L distance extra or less if you squeeze inwards. And so we talk about the strength of a gravitational wave as the distortion or the strain that it causes, which is that little L, the little distance, divided by the big distance. And the type of gravitational wave we measured in 2015 had a strength that it was delta L, or L over L, equal to about 0.0000000000000000000. I've lost track, 1. Scientists, of course, have a condensed notation for that, which I'll show in a moment. But in terms of trying to think about how big or small that is, it's about a comparison of the width of a human hair to the distance to Alpha Centauri, which is the next closest star after our sun. Okay? So it's pretty small. In our scientific notation, that's 10 to the minus 21. So it is this type of number that led Einstein back in his original paper to say these waves are just, whether or not, whatever's going on, they're just not going to be important to anything that I can conceive of in the future in terms of measuring them or astronomy or anything else. But they're a nice novelty. Now, in the 50s, as I say, people really began to understand gravitational waves better. It was at a 1957 workshop in Chapel Hill where people like Feynman and Zvi Perrin were gathered, and they talked about gravitational waves, and they figured out how to think about gravitational waves as actually carrying energy. The fact that they would deposit energy into a detector was an important feature. And so at that meeting, they also started to think about the question of whether or not stars in a binary system, so remember, we detected colliding black holes, that was a binary black hole system, whether stars in a binary system would be affected by the gravitational waves. About 15 years after that, Ray Weiss, he came up with an idea. He said, look, we've got this new thing called lasers. Lasers are really, really stable in terms of their frequency or their wavelength, and therefore we can use the wavelength of laser light to very accurately measure distances. He realized that if you just did it directly, it didn't work. You had to play a trick. And that trick was that you set up the lasers in a configuration that sort of a little bit mimics the image you saw with the yellow dots and the red one in the middle. So he put 2 mirrors. They're represented by the black dots here. So they're a pair of the yellow dots, the ones at 90 degrees to each other. He put a beam splitter, which is that little line there in the middle, and he shone a laser onto that beam splitter, split it apart, let the laser light go all the way down to the mirrors, get reflected back, come back into the middle, recombine, and check for interference of the light. If the arm lengths remained exactly the same, he'd tune it up so that the interference pattern gave him no light at what we call the dark port. But if a gravitational wave was passing, then the arm lengths would be different, and the interference pattern would actually allow light to be seen on the dark port. That's represented by this photodiode screen on the right here. So let's take a look at what this does. So there we go, there's the laser light reflected back, and you notice that it's dark on the screen, but then as the waves pass, the brightness of the light changes. Now we look at it in terms of waves, and the waves go out. They're going down the arms. There's initially no gravitational waves, so they come back and they interfere. And again, we're tuned so that there's destructive interference onto the dark port, but then the waves go by, as you'll see momentarily. So now the waves are about to go by. So as the length changes, what you find is that the interference pattern changes, and so you get bright signals on the photodiode. That brightness, the intensity of that light at the interference point, at the dark port, that's essentially what we measure. And in 1972, Weiss went through a calculation that showed what all the different things you needed to get right were in order to build a gravitational wave detector. Now, following on from that, in the mid-70s, he and Kip Thorne had a fairly pivotal conversation. At one point, Ray told me a story, which I was trying to remember when he told me this, and I couldn't. But he told me a story that there was a meeting in Washington, D.C., and he tried to get Kip to come out to it, but Kip wasn't enthusiastic initially, but then eventually he did come out. But by the time he went, all of the hotel rooms were booked up, so he just had him stay in his hotel room and took advantage of the opportunity to talk all night about how interferometers would measure gravitational waves. Now, this was actually an opportune moment. Kip had been looking for a way to change his research program at Caltech, and so he actually took on the goal then of building up a team that could build these detectors and eventually measure gravitational waves. So he got Ron Drever to move to Caltech from Glasgow. In 1982, they put in their first sort of presentation to the National Science Foundation about the detector. Then in 1986, they had a preliminary design of a detector you might build. They submitted a proposal in 1989, and they were finally funded for construction in 1992. So the timescales here are long, okay? So it takes a very, very long time to get things going. But the nice thing is that once that funding began to flow, Barry Barish took over the project of actually building the detectors. And as Stephen already mentioned, the detectors that were built are not small like the arm lengths you saw on the screen. These detectors have arm lengths that are 4 kilometers each. So when you see the picture here on the right-hand side, that's a picture in Washington State in Hanford. And the corner station down the right is where the laser and the beam splitter is. And to give you again the sense of scale, there's the cars parked in the parking lot outside of that building. The arms stretch out 4 kilometers perpendicularly, and they're covered by a concrete enclosure, but inside of that enclosure is a metal tube, which is in high vacuum. So we take all of the air and other materials out of it so that it doesn't cause scattering of the light. The basic structure, however, is exactly what Weiss had conceived of in 1972, and what I think of as sort of the schematic diagram is shown over here on the left. Part of the program built a second detector. The second detector was down in the southeast of the US, in Livingston in Louisiana, and that's an image of that detector. Now, I want to flip gears for a moment. I've told you about gravitational waves. I've told you about the detector that you use to measure them. But I want to go back for a moment, and I want to remind ourselves about these things called black holes, and also other things called neutron stars. So black holes turn out to be another prediction of Einstein's theory. When back in 1915, Carl Schwarzschild wrote down an exact solution of Einstein's equations to represent somehow the gravitational field outside of, say, a planet or a star. It had a peculiar artifact that took nearly more than 50 years to understand. There was sort of a funniness to it that if you made the stars smaller and smaller, eventually, if you took a star that was, say, equivalent in mass as our sun, so 1 times the mass of the sun, and you squeezed it down past 3 kilometers in size, okay? What you'd actually do is you'd create a sort of a hole, a part of space-time where stuff could go in, but nothing could come out. Now, it took 50 years to understand it, but in the meantime, a number of things happened. Oppenheimer and Snyder did a calculation which showed that stars, when they would die, would eventually collapse down and form these peculiar black hole objects. Penrose in '65 proved that that collapse was inevitable after a certain stage, that there was no way to turn it around, it would just always occur. And then in the 60s and early 70s, the first X-ray observations of astrophysical objects that actually emitted strong X-rays were made. And one in particular that is usually highlighted is Cygnus X1. This was a strong X-ray source, but it also was found to be a place where there was a star, a relatively large star. It was a blue supergiant. And when you looked at that star, you found that it was going around, it was wobbling. But you couldn't see the companion in ordinary light. You could only see the companion in X-rays. And so what was eventually figured out was that the companion was this very, very compact object that had about 5 times the mass of the sun and was pushed into a region of space that basically meant it had to be a black hole. So this was the first black hole, and as I say, a little diversion just to have that sense of what they are and where they come from. Neutron stars are a bit more complicated in some ways, easier in others, because they're still sort of stars. They're sort of spherical balls of matter. They were first thought of by Bode and Zwicky, who were trying to understand how supernova explosions, the big explosions that happen when a star has reached the end of its life and eventually tries to sort of runs out of nuclear fuel to maintain its normal behavior. Those neutron stars, again, thinking about how dense they are, for about 1.4 times the mass of our sun, the radius is about 10 kilometers, right? So that's like taking the mass of our sun, right, and squeezing it into, I don't know, maybe Greater Oxford. I'm not sure if that's quite right, but anyway, it's roughly that size. The conformation of these objects came about in the 60s. Jocelyn Bell, who's somewhere in the audience, I believe. There we go. Jocelyn Bell was the first person to actually notice and measure these pulses of radiation, of radio waves, coming from somewhere in space. And working in Anthony Hewish's group, they eventually showed and concluded that the pulses of radio waves were coming from neutron stars that were highly magnetic and were spinning very, very quickly. This was the first confirmation, really, a direct observation of a neutron star. And soon afterwards, in 1974, Hulse and Taylor, they actually observed a pair of neutron stars going around each other. One of them was a pulsar, and the other was you did not see the radio pulses. And so this little cartoon here shows an image of that. You've got the two objects, they're going around each other. The pulses in a pulsar come out like a lighthouse effect. And if they happen to pass across Earth, you see it like a pulsar. Whereas if it isn't passing across Earth, you don't see the pulses. Okay? Now, the interesting thing about all of this is Einstein's theory has now told you that in nature, there is a great recipe for gravitational waves. The first thing you do is you can get some stars. You can get them orbiting around each other, and that's common in the universe. And then you can wait until they die, and they'll either turn into black holes or neutron stars. And so you can get these very dense amounts of matter in pairs, what we call binary systems, going around each other. And as they do, they generate gravitational waves. So over the decades and leading up to the first detection, a huge amount of effort was put into theoretically calculating, using Einstein's theory, what would happen if you had a pair of black holes or a pair of neutron stars or a neutron star and a black hole. What would happen over time as they generated gravitational waves and as you let the system evolve. And so we're going to see here again a sort of a cartoon of a real solution of Einstein's equations generated with a computer, tracking a pair of black holes that are orbiting around each other. So early on, the black holes go around each other, they emit gravitational waves, and you see the strain signal being traced out in blue along the bottom. But as those waves are being emitted, they carry energy away from the system. And in physics, we know energy is conserved. So if energy leaves this system in the middle, something has to change in there. The energy of that system has to change. And the nature of gravity means that the only way to compensate is for the objects to get closer together. So I'm going to play that again. So as they get closer together, they also orbit more quickly, and eventually they crash into each other. So this is the dynamic process emitting gravitational waves of the collision of a pair of black holes. The interesting thing to look at the signal below is that you see that as it speeds up, it gets higher frequency and it gets higher amplitude. That's a characteristic chirp signal that comes from these systems. And the waves that we saw the first time correspond to just the very last few little waves right down here, half a second with a few cycles. So it turns out nature detected or gave us a recipe for gravitational waves. It turns out that actually this detection was made around 1050 here in Oxford on the 14th of September. And the nature of the signal you've already seen, but I'm actually going to trace it out here for you on the screen. So now I've overlaid the gravitational wave signal as it was measured both at Livingston and at Hanford. So the Hanford is the orange color and the Livingston is the blue. There's one slight thing done here. It turns out that there was just a slight alternation. There was a phase shift in the way the signals are. So they are slightly shifted. That's why the word shifted appears. But as you see, they overlay perfectly on each other just at the time, at the very end of that signal. This was a very important aspect of this experiment. We wanted to have two independent detectors very far apart that measured the same signal to give us confidence in what we were detecting. Now, the real question then is, how do we know it's a pair of black holes? And I've given you some of the hints already, but I kind of like this example here, going with one other thing. So the example here is we're going to listen to GW150914, which is marked with the ring, and also this other thing that's added by me. And if anyone wants to shout out a guess at what the second thing is, I'll take that in a second, but let's listen first. I'll play it one more time. Anyone? What's the second thing? No? Dog. A dog. That's great. Sometimes people actually come out with a suggestion of a frog. So nice rhyming there. All right. Well, actually, turns out.
Again. 1, 2, 3.
It's a set of people who are attempting to actually generate the signal that they just heard. And as you can tell, there's quite a difference, right? Now, the analogy then I want to make about how we know what it is to take another one, which is imagine yourself going out into the woods and you're walking along and you're listening. It's a nice quiet part of the countryside and you're listening and there are birds chirping in the distance. And you hear different bird sounds. And how do you know what those sounds are? Well, you know because you probably had a little book that told you what the sounds were and you listened and you put them into your brain gradually. And then when you're out in the woods, you match that signal that you put in your brain to the sound that you're hearing. But you have to compare all of the different guesses that you had, all of the ones that you had already previously stored up. If you hear a bird that you've never heard before, well, you might be able to say, that's a bird I've never heard before, but you can't say what it is. The approach we take to measuring gravitational waves is actually very similar to that. What we do is we say, okay, well, for these binary black holes and binary neutron stars, what we do is we make a big long list of all the possible sounds that could come from all the possible different configurations, depending on their masses, depending on their spins, depending on all sorts of things. And then we compare all that big, huge, long list to the data that we record. And we pick out the signal that matches best. And so that's what we did in getting the first signal. Now, what happened after the first detection? Well, I want to draw attention to the fact that this is now a global effort. So there was already a detector in Italy under construction, and there's also more recently been added a detector in Japan. So we now have a worldwide network of detectors. And since the first observing run, what we do is we go and we take periods of time where we turn on the detectors and try to measure gravitational waves. And then we take a break, and during that break, we make the detectors better. Then we go back to observing. We observe for a while, we measure gravitational waves, we take a break, make the detector better. And we just keep doing that back and forth. And so far, what we've done is we've gone through we're near the end of the fourth observing run. So the first observing run is when we detected made the first detection. The second observing run, I'll tell you a little bit about right now. It ended in 2017. The third observing run ran from 2019 till 2020. We had to shut down a little early due to the pandemic. And we're in the fourth observing run right now that started in 2023 and will end towards the end of this year. So what happened next? What's the next big thing that I want to mention? Well, on the 17th of August 2017 at 12:41:04, we measured another gravitational wave signal. This time, that signal was different than the first one. All right, so the first sound is the sound of a gravitational wave, unaltered. We just have filtered out some of the background noise, but that, when we compared it to all of our patterns that we already had pre-computed, corresponds to a signal from a pair of neutron stars that collided with each other. Now, neutron stars, as I said, they're kind of easier in some ways than black holes because they are matter. And so if they're going around each other, spiraling in really, really quickly, and by the way, just to give you a sense of this, at the very end, just before they merge, those two neutron stars, 10 kilometers in size, 1.4 times the mass of the sun each, are going around roughly at the speed of a kitchen blender. Okay? Now, so we know that that gravitational wave came from a neutron star. Up above it is a trace of gamma rays. There are a different class of photons detected with the satellite Fermi. The sound is not the sound of gamma rays. But what is interesting is that we found a flash of gamma rays just 1.7 seconds after the merger time for those neutron stars. And we were able to show that the direction to the gamma rays and the direction to where we thought the gravitational waves came from were consistent. And so we were able to associate those two things and say they both came from the same object. Now, that actually set in motion a couple of things. I was walking around Amsterdam at that moment and got a phone call to say that we had this very exciting discovery. And this is a photograph from some cafe that I had to sit down at and try and quickly connect to find out what was going on my laptop. But it also set off a bunch of observations with other astronomers. And about half a day, about 12 hours after the gravitational wave had passed, a group of astronomers using a telescope in South America detected an explosion in a galaxy called NGC 4993, which was about 120 million light years. Compare that to the 1.3 billion light years of the first event. This was much closer, and you can see in this is actually going between two images. The first one, where the little thing near the arrow is bright, is the discovery image for the explosion. And the latter one, which is the one it rests on now, was an image taken 4 days later, showing that explosion had dimmed. Okay? So this was the first multi-messenger observation of a collision of neutron stars. In some respects, gravitational waves brought the sound to what was the movie of gravitational wave collisions. So now we were able to know what happened to that neutron star binary for about 30 seconds before the two of the things collided. We were able to know what happened in the instant around the collision, through the gamma ray burst emission. And then later, after discovering the explosion, astronomers from all over the world began observing this object, and were able to stitch together a huge amount of information about what happened after the two neutron stars collided. Just today, this afternoon, we sat through a wonderfully exciting session, actually, which it's pretty common at these meetings to go back to GW 170817 and talk about the new things and the great things we discovered. And so we spent a great deal of time listening to exciting new results coming in, where people are beginning to model even better what happens when this collision happens. The cartoon here is not something I want you to think of too many details about, but it's just to sort of capture this idea that when the neutron stars collide, there's a big explosion, but it also turns out that that collision, that matter all stuck together, is too massive to remain a single neutron star, and it collapses down to form a black hole. Some of the matter that's involved in the collision gets sprayed out into the universe, and a whole bunch of different things happen. We get the gamma rays generated, we get light generated, we get new elements created. So while we know hydrogen, helium get formed in the early universe, we have a lot of elements on our periodic table, and we've worked out through the years how they get to form in our universe. But for a long time, the ones that are on this part of the periodic table, color-coded as yellow, we weren't fully sure of where they were coming from. To be honest, that's a signal that I'm getting late. To be honest, we're still in some ways not sure. Today, we were listening to a lot of talks that were trying to understand the details of what material and what's happening inside of this explosive area. And we're just beginning to get a sense of it. Now, since then, as I said, we've gone through 2 more runs, more or less. We've gone through the third observing run and then the fourth. And this plot here is one that I'm going to use for most of the rest of my time to give you a sense of what else we've found out over the last decade. So on this diagram, it'll take me a moment to walk through it, to lead you through it. The horizontal, don't worry about that. That's not actually got any values on it. It's just a way to spread out the dots in some way. And we've chosen to spread them out in this lovely structure whereby they seems to be welcoming you in. And it's quite a nice little design. I'm going to stay still after this reconnects. Yes, that's the other signal. So on the vertical axis are masses. So they start at the very bottom. They're at 1 times the mass of the sun, 2 times the mass of the sun, 5, 10, 20, 50, 100, 200. Each dot represents either a neutron star or a black hole. And so the neutron stars in the yellow down the bottom are the neutron stars that are primarily observed using radio pulsar observations, like the very first one. The red on either side, those are things that are measured in X-ray binary systems like Cygnus X1, and are massive enough that we think they're black holes. And so back at the end of the second observing run, what we had was all of these things that were neutron stars detected by radio. We also had the black holes detected by X-ray, and we have these weird triplets, right, of dots. What they represent are two black holes, or two compact objects, that collide with each other to form a third. And so if you look at the ones higher up, you'll notice that there are two things that are kind of, the first detection actually was something that was around 30 solar masses, 30 times the mass of the sun. Both objects were close to that. And then they collide to form something that's about 60 times the mass of the sun, a black hole. Down near the bottom here, you see what was GW 170817, which has the two neutron stars that collide with each other to form something that's around 2.8 solar masses. We don't know if that's a black hole or a neutron star for sure. We think it's probably a black hole, but we weren't able to determine that from the data. I'm going to move slowly. Now if we move on to 03, you notice that by improving the detector, we now are able to detect more of these things. We're more sensitive to gravitational waves, so we see more of these collisions. And so now you see that the black hole region is filling out. If you look really, really carefully, what you'll notice is that there's two objects down the bottom that have two yellow dots going to this mixed blue-yellow. So there's the one which was GW 170817, but there's one over here which is 190425, so it was measured on the 25th of April 2019. And we have a set of dots that are new. They're the ones that are the yellow dot paired with a blue that then turns into a blue. So it's a little hard to see. You have to squint, you have to really look carefully to be able to see where the different points are coming in from. But that means that we got the collision of a neutron star with a black hole. Strangely enough, when you search for pulsars in our galaxy, you do find quite a few binary neutron star systems. So two neutron stars going around each other. But we've never seen a pulsar going around a black hole. And so when we first made these measurements, whereby we actually did detect the collision of a neutron star with a black hole, it sort of filled in that gap, which we expect should exist, but for some reason we've not found any such pairs in our galaxy. Now, just last week, we released results from the first 1/3 of the fourth observing run, and you can see now we're really beginning to fill out all of the black holes. There's way more black holes now known through gravitational wave observations than there were ever known through the electromagnetic. The neutron star region, not so much. Nature was very kind to us with the 2017 event, and it turns out that since then we've got one possible, the 1904-25 event, but we have no others observed in the fourth observing run. So we're sort of curious. It feels like something's going on, and while nature was very kind with the first event, which came right at the beginning of the first observing run, and was very kind with the second event, or with the neutron star collision being something that was there towards the end of 02 and was very nearby. It's just not being quite as kind at the moment with neutron stars. Before I finish, I want to show you another look, a slightly more scientific look at the same data set. So the previous one is to give you a sense of what we've done and what we've learned. While this one here is something that we use to begin our studies of understanding what we call the populations of binary black holes, binary neutron stars, and neutron star black holes, binaries. So each dot on this represents one of those collisions. Okay. So what you've got is you have what is the heaviest object in the pair that collides, represented on the horizontal axis. On the vertical axis is the lighter of the two objects. And so each point corresponds to a heavy mass and a lighter mass that collides with each other. Some of them are close to equal, of course, and that's fine. But now, one of the things that we want to do is we want to figure out how many of each kind of object is there in the universe. And you can actually begin to do that by sort of squinting at this diagram. So when you look at it, your eye is probably immediately drawn to a few features. One that draws my eye, at least, is right here in the middle. So you've got somewhere around this 10 solar mass pair that you've got this little cluster of collisions that we've measured. You can see that as you go up to the higher masses, there's sort of a little gap. And then you've got this second, bigger cluster of collisions that we measure. If you look down at the lower mass end, so the neutron star range, that's down this sort of bottom swath that's from 1 to about 3 on the vertical, and then going across, depending on if it's bigger than 5, we think it's a black hole. And you can see we're filling in a few, but not too many. There's a couple of features that are also interesting in this. The first one is down this lower end in this rectangle. If you look at that, you'll notice that there's actually no compact object pairs that we detected in there. So there's some sort of a gap between the neutron stars that are down at the bottom of this diagram and the black holes that are above it. A similar situation is observed with the electromagnetic masses. So this is not unexpected, but we still don't know if it's real. We don't have enough of these objects yet. Also, if you go to the higher end, you actually also can see a similar thing. Up there, there's sort of a more pronounced thing going on. Inside of the rectangle, there are several dots. So there's clearly stuff in that rectangle. But if you flip it over to take a look in the region between 50 and 100 over here, you'll notice that the count, if you go this direction, is much higher than the count if you go in the rectangle going across. This is a sign that there's something different about those systems where the heavier mass objects tend to go into that region, whereas the lower mass objects do not. So with that, I'm going to end with a little look forward to let you know what else is happening and where we're headed. So the International Gravitational Wave Observatory Network is going to continue observing into the 2030s. There's plans for upgrades that will occur over the next 5 years and then even over the next 10. When we bring the detector that is currently under construction in India, when we bring that into the network, which should happen sometime in the early 2030s, that's going to really help us out with disentangling information about each of these collisions. In particular, it will help us say where on the sky those collisions are more likely to have come from. So all of that's going to be going on. Of course, in parallel, there's going to be the observations that are made by electromagnetic astronomers to try and associate explosions on the sky with the gravitational wave signals. But then we also have the opportunity now that we've measured gravitational waves to start thinking about other different types of signals. I've only told you about this very special class, but there are other things. Anything that involves a lot of matter getting squeezed down and shaken around really, really vigorously is going to generate gravitational waves that are strong. So we could get gravitational waves from the very early universe, the Big Bang. We could get gravitational waves from supernova explosions. We could get gravitational waves from the cracking of cosmic strings. All of these are things we go looking for. As yet, we haven't found them, but as we make the detectors more sensitive, we hope we will. But you can also start to think about looking in different frequency ranges. So you can build a detector in space with million-kilometer arms instead of the 4-kilometer arms here on Earth. And there's an experiment known as LISA, which is being led by the European Space Agency, that is intended to launch an interferometer. It's a sort of a triangular configuration into space in 2035. That will be sensitive to black holes that are not like the ones I was telling you about here, which are 10 and 20 times the mass of the sun. It'll be sensitive to black holes that are 10,000 or 1,000,000 times the mass of the sun. So we'll learn a huge amount by changing that frequency and looking for those objects. There's also a fascinating experiment that I gave its first tentative results a few years ago, and that is what we call pulsar timing. It's represented by the little cartoon down here, where you see a radio telescope pointing out into the universe with a pulsar and so on. Well, by taking a look at pulsars, these are very, very precise clocks. And so by looking at different pulsars, you can actually tell if a gravitational wave is passing across the galaxy. The frequency of those waves is very, very, very small. Okay? So these things tend to be sensitive only to the most massive pairs of black holes colliding, tens of millions to hundreds of millions of solar masses inside of the black holes that collide with each other. And then we look to the very future, to the next generation of ground-based detectors. There are two concepts under consideration. One is the Cosmic Explorer combination in North America, and the other is the Einstein telescope here in Europe. Both of those will increase the sensitivity to gravitational waves by a factor of 10, so you'll be able to measure 10 times smaller strain. And in particular, that translates into increasing the number of binary black hole collisions that we'll measure by 1,000. We will essentially be able to see all of the collisions across the whole universe once we get those detectors built. So hopefully they'll begin to be built in the 2030s and be operating by the 2040s. Thank you.
Thank you, Patrick. Wonderful talk, fascinating. And we'll got time for questions from the audience or anyone online. We've got one right up at the back here. Well, we'll take one here, and then if you go right up the back there, you're there.
Yes.
Good afternoon, Professor. I am Gonzalo, a student from Steam Talent Research Institute in Spain, and I will ask a question related about two black holes near. We know that Hawking radiation is produced when a pair of particle and antiparticle are one of each attracted to a black hole with a negative energy. So that is evaporating the black hole. So my question is, if we have two black holes near and the horizon event is tangent at one point, if that case happens, each particle will go to another black hole. So it could emit Hawking radiation, and in that case, how we could know which black holes evaporates and which gain mass?
That's a great question. The first thing is that the Hawking radiation we think will affect both black holes. We actually think it will affect both black holes the same way. They will each evaporate or attempt to evaporate. The analogy that you're talking about, the pair production, that whereby you get a negative energy and a positive energy, and the positive goes to infinity and the negative falls into the black hole, that is a picture developed in order to gain some intuition for how this Hawking process works for a single black hole. You're exactly right that if you have a pair, if this analogy is the right analogy, then you could get what you're describing happening some of the time, which would mean one of the black holes would get bigger and the other get smaller. So you'd move them around. But of course, if you keep the analogy, well, if it happens once going one direction, it has to happen going the other as well. There's no reason why it wouldn't. Okay? So on average, you'll actually get the evaporation happening because the things will still move to infinity. The last piece that I want to mention for this is that the thing about this is that the time over which, or a length of time it takes for a black hole of this size to evaporate compared to the length of time it takes for one of them to collide under gravitational waves. Okay? The length of time for evaporation is much, 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 much longer, because the more massive the black hole, the lower the temperature, and the slower it evaporates. So in fact, we wouldn't see that effect at all in the black holes that we're observing, because their masses are too big.
So building on that question, actually, that's a great segue to my question, which was, is there anything that gravitational waves can tell us about what happens at the event horizon, or some sort of black hole information paradox that we can constrain from these observations?
Another great question. So let's try a couple of things here. So what is definitely true is that because we have these pairs of objects or black holes going around each other, they sample space-time close to the event horizon of the black holes. And so some information about the space-time structure near the event horizon is captured into the waveform as it comes out and we measure it. At our current sensitivities, we don't, and for the types of signals we're seeing, we don't currently have a concrete example of something that will really probe the horizon. What we do know is already, because of the frequency of these waves, we have a sense of how big the black holes have to be, because the minute they touch, the waves shut down. Okay? So we do learn, in a sense, about the size of the waves by taking a look at the frequency where the waves stop. Okay? So, pardon me, the size of the black holes because of that. But there are other things we're trying to do. We actually ask questions of whether or not the signal that we calculate, remember I told you we made this big millions of waveforms that we compared with the data we measured. And we now say, okay, well, let's check that the signal was actually one of those and not just something that was close to them. So we look for things that are slightly different. We look for deviations from the examples we calculated. It's analogous to going into the woods and you hear some bird that chirps and it's like, oh, that's like, but it's slightly different. And that's what we're looking for. We're hoping sometime to get that slight difference that will then tell us that something's not quite right with Einstein's prediction, hopefully. Could be astrophysics. But we're not there yet. And so hopefully in the future.
Good afternoon, Professor Brady. My name is José Antonio, and I am a student at STEAM Talent Research in Spain. Since light cannot escape from black holes, my question is, what does actually happen to photons inside? And is it correct to imagine that light accumulates infinitely within the black hole, or does general relativity describe a different scenario?
Another interesting question, one close to my heart. My research as a PhD student was on the inside of black holes. So what we know at the moment is that when the black hole forms, it does seal off the material that's inside of the event horizon. If you put that black hole in empty space, it will eventually evaporate. But the difficulty we have is when we use Einstein's theory and solve the equations, what we find is that inside of the black hole, in fact, to the future, it isn't actually a place, it's not a place in the middle, it's actually a time in our future where you get to, and the curvature gets so big that it is no longer, we think that gravity would no longer be described by Einstein's theory. Anything that goes inside the black hole has to arrive at that time. It has no alternative. Doesn't matter how powerful a rocket you strap on your back, you cannot get back outside of the event horizon. Okay? So what we know is that Einstein's theory tells us that eventually inside of the black hole there will be this time where that happens. The question becomes, what have we not understood? What theory should we be using to describe that? because you don't expect things to get infinite. And that's what Einstein's theory would tell you happens there. So it's a mystery yet what the answer actually is. And doing evaporating black holes doesn't help us, it turns out, because you end up still with this problem that there's a time when the curvature or the gravity is so strong that Einstein's theory no longer works.
Okay, we have time for one more question.
Thank you, Professor. You mentioned the LISA program in the last, where we can put the interferometer in the space, and each arm is, has length of millions of kilometers, so which is much more sensitive. But why do we need such a sensitive device to probe the supermassive black hole? Because in the beginning you showed that the signal is proportional to the mass. So why is the mass higher than you will need a more sensitive one?
Great question. So I've already mentioned a little bit of the answer, in fact, and what I said was that the waves from a black hole collision, they cut off at a frequency that is related to how close the two black holes are together. Well, the thing is that as you increase the mass of the black hole, its size goes up proportionally. So how close together it can get is bigger, right? So you can even use Newton's theory to calculate this. The orbital period, or the free orbital frequency of the two black holes, when they're separated by a bigger distance, is lower. So as the masses of those black holes go up, the highest frequency content in the gravitational waves goes down. Okay? And I'm going to this is the only time I'm going to look back through my slides, but I just want to show you this because there we go. So there's a representation of frequency on the horizontal in that left diagram where the blue and the red curves are, and vertical is strain. And what you notice is there's a bucket, okay? And the lowest strain noise is at about 100 hertz in that. And so we're very sensitive to black holes that have sizes up to, it turns out we can go up to hundreds of solar masses, but sort of 20 or 30 solar masses is actually a very, very sensitive band for us. As the mass goes up, the frequency of the waves, the highest frequency, moves down. And eventually we're not sensitive to them. So we need to build a detector that is sensitive to waves at lower frequencies in order to measure the higher mass black holes.
So thank you, Patrick. This is an area which has really revolutionized astronomy and physics, and the two discoveries that you mentioned, they were one of those occasions. I can also, although I wasn't even involved in the experiments, I can remember where I was at the time the discoveries were announced. Yeah. And given the results you've shown for this observing run and the upgrades to come, I'm sure there are many more discoveries in this field that we will see. So thank you again.
Thank you.